So I know in the last video I mentioned that we were going to move on to cylindrical coordinates, and we will, but I made the choice that instead of kind of diving deeper into working on triple integrals, that now that we kind of understand what a triple integral is and we understand how to tackle it over a variety of regions of these 3D these 3D regions of integration, I figured it'd be a good idea to touch back on the same applications that we had done for double integrals, which was center of mass and also probability. Okay, and it kind of should follow pretty easily from all the talking that we did in the double integrals lectures, especially regarding center of mass, where in 2D, right, we had what we called a lamina, and we said if you have some sort of lamina here, then we said to find the center of mass for every single point, you essentially have to calculate the moment about the x-axis, which was basically equal to the distance of that point from the x-axis times the mass at that particular point. So maybe I'll just say xy, right? And then you also had to calculate the moment about the y-axis, and that would give you kind of like the heftiness, the weight of that particular point about the x-axis. And we did this for every single point, and so this formula just quickly became that the total amount of moments, right, of every single point, basically the total heftiness of every single point about the x-axis was simply, you could just do it, it's the distance of that point from the x-axis. Now, for us, mass wasn't usually given to us, and what was given to us was a density function for our shape, and then dA. And remember that this little tidbit right here, the density over a small area, this is our mathematical interpretation of mass at a point, right? You have a tiny little point with a tiny little dA around it, and you calculate the mass at that point by doing density times area. And so that was our moments in the x direction. Our moments in the y direction very similarly was, the distance from the y-axis times the mass, or in our case, times the density dA, right? And those were the total moments in each particular direction. And so we said, okay, well, if this gives us, the total moments, right? This gives us our total moments. And remember that x is a unit of distance. Maybe we'll just say, just to have a unit to go with, maybe this is in inches, and this is mass. So let's pretend that this is in kilograms. Whoops, the Europeans are turning in their graves right now. I'm going to choose centimeters instead of inches. Right, I probably should choose meters, but whatever. But let's say this is in centimeters per kilogram, right? That this is our total moments about the y-axis, right? So if I want to figure out the average distance that I need to go, right, in the x direction, what I do is I divide this by the total mass of the object, right, which is in kilograms. So divide this by m, and this gives me what we called x bar, right? And this was the average x coordinate. Okay, and it made our units, this is in mass. So this would be, this is in centimeters, because the kilograms and kilograms canceled. So like this would be in centimeters, right? And that tells me how far from the y-axis do I need to be. So it's a little confusing. It almost seems a little backwards, but remember that this is the average distance from the y-axis, which is represented with an x coordinate. Okay, and then very similarly for y. So the upgrade for 3 dimensions. Okay, so in 3D. Okay, in 3D, perhaps we have some sort of 3D region, and maybe I don't know, what could it look like. We could make it look kind of interesting. let's make it look like this block. Okay, so that's our 3D region. So now it should kind of make sense in a way that we're going to extend this into 3 dimensions. And sure enough, we upgrade what we're doing to the following. So the moment, so they do moments, so YZ, and I'm going to explain what all of these are in just a second. Moments, what's this one going to be? It's going to be XZ. And now we have a moment about the XY, okay? And so each of these, right, I'm going to write down kind of the loose thing before I put integrals in front of this, right? Basically, in order to find the center of mass of an object like this, right, for any given point, I have to figure out the moment, basically the total weight that this point carries, you know, in terms of being far from the YZ plane, which is its X value. I have to tell how much weight it carries, right? Its moment that it carries as a distance from the XZ plane, right? Which is the Y value of this coordinate. And then I also have to figure out how much weight this point carries from the XY plane, which is going to be its Z value, right? The Z value of that point, right? Obviously all scaled by the mass at that particular point. So all this to say, right, this moment, this notation, this M sub YZ is the moment about the YZ plane, which again, this right here, I guess I should have used proper colors above. This right here is going to be the distance X from the YZ plane times what? Well, it's going to be the mass of the point, right? So the mass at that particular point, X, Y, Z, okay? How much leverage, how much of a moment do we have about the XZ plane? Remember, this is X, this is Y, and this is Z. How much do we have about the XZ plane, which is over here? Well, that's going to be Y, right? The Y distance of the point times the mass at that point. And then last but not least, if we want the moment about the XY plane, that is going to be given to us by Z times the mass at X, Y, Z. And so, you know, this idea should make sense that we have to check basically how much leverage, how much weight, how much of a strain is it putting on this object relative to all 3 directions now, right? In 2D, we only had to check 2 directions, and now in 3D, we have to check 3 directions. So just like before, we can generalize this to say, if I want to know the total moments about the YZ plane, then what are we going to do? Well, for every single point in this object, let's call this object E, right? For every single point in this object E, we have to calculate the total moments, right? We're doing the total moments of all points. And then, yeah, on our object, right? On our object. With respect to the YZ plane. Okay, what is this going to equal? Well, it's going to be the triple integral, whatever it is that defines that region E. And then the total moments here, well, that's just going to be, again, just the distance X times, now again, mass is density, and we would need to be given a density function for this object because in theory, the density is different at every single point that I take, right? If the density was constant, our calculation would be a lot easier. But because this is a Calc 4 class, our density is usually variable, which kind of makes sense. Most objects are. And then times dV. And remember, just like before, this right here is the mass. It's our theoretical mass of a 3D point, right? Over some tiny, tiny, tiny volume, right? Over a tiny volume. Okay, and this process is iterated for the rest of them. So m sub xz, basically the moments about the xz plane, well, that's going to be a triple integral. But now at the head of our calculations, we have y times our density function dv. And then for the last one, we have the moments about the xy plane, which is going to be the triple integral, right? We need to describe the entire region. And then it's going to be z times rho of xyz dv, okay? And so those right here, these right here give the total moments of all points inside of our object here. And that's super useful because the center of mass, right, is going to be, what we really want is the average, right? So remember, to get the center of mass, we take the average. Take the average of all the moments. And so what does our coordinate point look like to get the center of mass, right? It's going to be some 3D points. So there's going to be an x value, a y value, and a z value. How do we get it? Well, let's see. So let's take a look at it. So if we want the x coordinate, right? If we want the x coordinate, looking at our drawing, that means we're looking here, right? We want to figure out the average x distance away from what? Well, from the y, z plane. That's going to be this calculation right here. And so if we do this, that means we're going to take this and then we average it out over the total mass like so. How do we get the average y coordinate, right? So we'll be looking at the y calculations next, right? The one that's giving us the y, that's the one from the xz. And so we would take whatever we get for that triple integral there, m sub xz, and average it by the mass. And last but not least, not much to do. If we're trying to get a z value, we're going to do m sub xy over our total mass, like so. So far, so good? So that's going to give us the center of mass for this object. Pretty straightforward extension of what we've done. And hopefully at this point, we're kind of noticing that this is going to be a trend in this class. When we have learned to do something in 1D and 2D, we extend it to 3D because 3D is pretty much where a lot of magic happens. And in theory, you could do this to higher dimensions as long as you have a proper way of framing your argument and describing what it is you're talking about finding the center of mass of, right? What does a 4D object look like? But yeah, you can do stuff like this. So that's center of mass in a nutshell. Probability is even easier. Probability. So again, now, right? So now we have a probability function. I called it a probability density function. Slightly misspoke. Probability density function is for specifically of one variable. They call it a joint probability density function, but probability density function, I don't know, interchangeable for me, but I'm not a statistician. So we have we call it joint probability density function. Density function. And this is nothing unlike what we had before. Guess what? Instead of being based on one variable or two variables, we have this thing, f of x sub y sub z, and it's based on these three variables that determine the outcome of some event. And, it has the property that triple integral over basically all of the x, y's, and z's. So I guess I should maybe I'll abuse notation. I'm just going to put fat minus infinity and a fat infinity up here. I've never done that before, but it's the right idea, it saves me from writing it all out. Basically, that if we add up all the total probabilities of our event happening over our entire domain of x, y, and z, this should equal, you guessed it, 1. And that is literally the extent of what we're doing. So now if the question is, what's the probability of passing the class based on your GPA, based on your height, and now we can throw in one more variable and say, based on your score in your history class. Right now we just have 3 variables. We can just keep adding in variables, and as long as we sustain this property, right, where we would be given this function, right, this would be given to us, and we would be asked to find the probability of something happening, essentially. So notice I'm not even diving in and doing examples, because there's only actually 1 or 2 examples, I think, in your homework. There's not really that many, and it's not a huge focus in this class, and I firmly believe that even if you are having any issues like grasping this concept, just hop into section 15.6 in the textbook and just scroll down. Even the textbook only has 1 example to go off of, and the reason is because the extension from what we've been doing is pretty darn straightforward. So that is probability and center of mass in a nutshell and triple integrals. Hopefully it seems even easier than when you learned it for double integrals. And the next thing that now I promise is so now, we've been doing triple integrals over these rectangular regions, and we did them over some generic looking regions, and now we're going to do it for another specific type of region. So